2011, Lab 5 by Connor Lin. Now, the introduction. The main purpose of this experiment is to analyze data from a slinky dropped from a static equilibrium and compare it to a computational model. The main concepts of this experiment is Newton's second law, the gravitational and tension force, and velocity and position update formula. Now, the main methods of this experiment is an analysis of the motion of the slinky in the video in the tracker application, and then determining the conditions and constraints and GlowScript coding to calculate our computational model. Results. The computational model fits experimental model very closely. Now, the main concepts in this experiment are Newton's second law, which is force equals mass times acceleration, or delta momentum divided by delta t. We also need the velocity update formula, which is Vf equals velocity initial plus F net times delta t divided by mass, and the position update formula, which is Rf equals Ri plus Vf times delta t. Now, we also need the force of gravity for this experiment. The force of gravity is the vector 0, negative mg, 0, and the force of gravity for Earth is negative 9.8 meters per second squared. Now, for this model in the system, it's the mass of the slinky and gravity, and the surroundings does nothing. We assume that there are no external forces acting on the system. Now, the initial conditions is at top is at the origin with 0 net speed, and the bottom is negative 1.254 meters 0 net speed, and the force of gravity is 9.8 meters per second squared. We assume that the bottom is this height as we took the average height of an Australian mare and subtracted some height for the slinky. Yeah. So as you can see here, this is the man holding the slinky, and at the top is the top of the origin, and when it's stretched all the way to the bottom, that is the bottom of the slinky. And we use this video and we put it in the track application to track the position, and we can use that to calculate a model. Now, after that, we went to coding. Now, we set up the visuals and the graphing with the start and origin of the sphere and the bottom. Now, once we had that, we went on to the spring. We set up the parameters for the spring and the position. Now, we assume that the mass of the slinky is 0.02 kilograms. Now, we set up the positions of the start and the bottom of the slinky at 0, 0, 0, and 0, negative 1.254 meters, and 0. Now, the spring of the axis is the bottom of the position of the bottom minus position of the start. Once we had the time parameters and the gravity, force of gravity, we wanted to move our calculations in the code. Now, so we had the force of gravity, which is the negative mass times gravity times j hat, and the force of tension, which is negative mass times gravity times j hat. Now, we used GlowScript coding to calculate the start of the velocity and the velocity at the bottom, and then we used these two velocities to update the start of the position and the start of the bottom. Now, once we had that, we plotted the position curve compared to the time. So I can see this is on the left is the computational spring position versus time, and on the right is the experimental position versus time. The main result is that experimental computational graphs are very similar. Now, what if we stretch the slinky above the origin? So although the values would be flipped, it would still follow the same pattern. Now, what's mean at the bottom of the slinky if there's an additional stretch? Now, we only factored for the force of gravity and tension in this experiment, but in real life there are other factors such as drag that could potentially stretch the slinky more at the bottom. The main conclusion is that the computational model matches the experimental model. Thank you.